Previously in Chapter 12, we've gone over sound waves. In this segment, I'll move on to discuss sound intensity and resonance. Sound intensity is defined as the rate at which energy flows through an area perpendicular to the direction of wave motion. So in other words, sort of how fast the sound spreads, or how intense it is. So because intensity is a rate of energy transfer, that's power, which I have shown with this P, and then it's divided by area, because there's some area perpendicular in this perpendicular plane through which the sound is moving. That's A. So if intensity is P over A, the units for that are watts per meter squared. And then since we know that sound waves are actually spherical in the real world, and intensity is still pressure over area, the area of a sphere is 4 pi r squared, that's the surface area. So we'll rewrite intensity for spherical waves as power divided by 4 pi r squared. That's how we'll solve for the intensity of a sound wave. R is defined as the distance from a source, so intensity decreases as distance from the source increases because intensity and radius are inversely proportional. The intensity of sound waves also determines which sounds are audible and which are not. Most sounds that humans perceive fall between the threshold of hearing and the threshold of pain. The threshold of hearing is the softest frequency or the softest noises that can be perceived by the human ear. These are usually close to an intensity of about 1 times 10 to the negative 12 watts per meter squared, so fairly small. Then the threshold of pain is the loudest sounds that humans can tolerate without also experiencing pain to the ear. That's about 1 watt per meter squared, so sounds will often fall between these 2 points. We learned from before that frequency determines the pitch of a sound. Intensity is also important in that it determines the volume of a sound. This is known as relative intensity, which is the ratio of the intensity of a sound wave to the intensity of the threshold of hearing, which I went over on the last slide. This is expressed using the decibel, which is the unit for relative intensity. Intensity is not directly related to the volume of a sound. Rather, it's a logarithmic relationship. So when the sound goes up by 10 decibels, rather than increasing by 10 in intensity, the intensity multiplies by 10. So for instance, if the sound started out at an intensity of, we'll just say 4 watts per meter squared, although that's unrealistic. If we increase this by 10 more decibels, the sound would go up to 40 watts per meter squared in intensity. Some sound waves also result from forced vibrations. These occur when an object sets another in motion. So for this we'll use the example of a guitar, where when you pluck a string, it causes the bridge to vibrate, and then, as a result, the body of the guitar receives these sound waves and can transfer them to the air more efficiently than the strings, because it's a bigger object. These are also known as sympathetic vibrations, which are when objects vibrate as a result of one another. Even in situations with forced vibration, each object has its own natural frequency. This is the frequency at which an object will vibrate most freely or naturally. So you may have seen before in your physics classroom sort of a setup with tennis balls on flexible rods. When this entire system is set in motion, so a person moves this base back and forth, causing the tennis balls to vibrate, the frequency of the system's movement determines which tennis ball on a rod will vibrate the most freely. So the tennis ball that's vibrating at natural frequency at a certain moment will have a greater amplitude, or you'll watch it vibrate more back and forth on its rod. This condition is known as resonance, which occurs when the frequency of a force applied to a system matches its natural frequency. And as you can see, these two lower tennis balls are sort of at the same level, which would mean they have similar natural frequencies. So when the system vibrates at those tennis balls' natural frequencies, they would move back and forth most rapidly. Similar vibrations to the forced vibrations I discussed earlier cause nerve impulses in the human ear that lead people to hear. When you hear a noise, your eardrum, which is about right here, will vibrate, transferring that motion to the hammer, anvil, and stirrup, which are small bones in your middle ear, and then finally into your inner ear, which sends impulses to the brain. So that's how hearing works for humans. With this information about sound intensity and resonance in mind, here are some practice problems. Number 1. When the decibel level of traffic in the street goes from 40 to 60 decibels, how much greater is the intensity of the noise? So we learned that an increase by 10 decibels leads intensity to increase by 10 times. So we'll have 10 times intensity for each 10 decibel increase. In this case, we're going from 40 decibels to 60 decibels. So that's an increase of 20 decibels, which means that intensity will multiply by 100, making the sound 100 times as intense. Number 2. Calculate the intensity of the sound waves from an electric guitar's amplifier at a distance of 5 meters when its power output is 5 watts. So for this, we'll use our equation for intensity, where intensity is equal to power over 4 pi r squared, again because sound waves are spherical. So we're looking for intensity. We know that the power output is 5 watts and that the r is 5 meters. So we'll plug in all of those numbers, 5 squared, and simplify to find that the intensity is about 0.0016 watts per meter squared. And that makes sense because 0.0016 falls between the threshold of hearing and the threshold of pain. So this would be a sound that's perceptible to the human ear. Number 3. If the intensity of a person's voice is 4.6 times 10 to the negative 7 watts per meter squared at a distance of 2 meters, how much sound power does that person generate? So again, we're looking at the intensity equation, where intensity equals power divided by 4 pi r squared to represent a spherical sound wave. This time we know the intensity, which is 4.6 times 10 to the negative 7th. We're looking for the power, and we know the radius, or the distance. That's 4 pi times 2 squared. So if I multiply this 4 pi times 4 all the way over to the other side, to isolate the p, we get that power is equal to 2.3 times 10 to the negative 5 watts. That's the power output of the person's voice.